Well, hello, everyone. My name is Jim Lewis. I am the Chief Architect of OSVVM. I'm also the IEEE 1076 VHDL Working Group Chair, and I'm a VHDL training expert at Synthworks. We're going to be talking about OSVVM in a nutshell. What is VHDL's #1 verification methodology? So if you're looking for an alternative to System Verilog because you have a VHDL design house, you've come to the right presentation. All right, so what we hear from many people in the crowd is why VHDL? Well, if we look at the Wilson Research Group 2022 Functional Verification Survey, sponsored by Siemens, we see that for FPGA design, 66% worldwide use VHDL. And for FPGA verification, 56% worldwide use VHDL. That means VHDL is the #1 FPGA design and verification. Note, I was careful about that. ASIC, it is System Verilog. All right, mostly, except for Europe. Now, what about OSVVM? Well, worldwide, same survey, 28% use OSVVM. That's roughly 50% of the VHDL FPGA users use OSVVM. Okay, so that makes OSVVM VHDL's #1 verification methodology. All right, so what is it then? Well, it's a verification framework, and it's good for your unit level test benches, your small RTL blocks, as well as your large system full chip, multi-chip simulation environment. It's a verification utility that plugs the gaps in VHDL and brings VHDL up to a full verification language capability. So we have constrained random, we have scoreboards, functional coverage, memory models, efficient implementation of memory models, so we have a sparse memory model in there, error tracking, and message filtering. We're a verification component library with a growing set of verification components. We're a scripting library, and it's a layer on top of Tickle, which all the tools implement, or your shells implement in your Linux OS, okay? And we're a co-simulation capability. We can run software on top of the hardware in a simulator, or if you wish, write your tests in C++. And then we're a test report generator. And this is one of the big selling points too. We produce HTML-based test suite, test case, and log files, okay? And we'll take a look at those towards the end of the talk. We also generate the JUnit XML for the continuous integration, continuous delivery tools. OSVVM is free open source, and it's developed by the same VHDL experts who have been helping for years with the VHDL standards. We have a long history. We actually started in '97 in Synthworks' VHDL classes. About 2010, 2011, we introduced the random package and the coverage package as open source. That's basically our genesis in formal open source. About 2016, we got onto GitHub. And then we've been growing, and definitely during the COVID years when I wasn't traveling, we had a lot of rapid growth as far as capabilities go. As a framework, we look pretty much identical to what System Verilog and any other verification framework does. We use verification components to implement interface signaling. We have a test sequencer that calls transactions and creates our test cases. Each test case then is a separate architecture of test control. So the framework, it's nothing more than structural code, just like what you do with RTL. We instance the dot, we instance our verification components, and we instance our test sequencer. It just plugs together in a very natural way. Okay, so how do we build pieces? So let's start with the verification components. We have 3 basic steps to building our verification components. Step 1, we have to figure out how to connect things. And for that, we're going to use a transaction interface implemented as a record. Step 2, we need an API. We don't want to just be wiggling signals. We want to be abstractly talking to things. So we create an API for it. Step 3, we build out the verification components. Okay. Okay, so the transaction interface is nothing more than a record, okay? And types in record, that's a pretty basic VHDL thing we've had since '87. Okay, but the record's in out. So we have some magic in the types in the form of resolution functions that allow us to do this, that make it actually, don't just allow us to do this, make it simple so that you don't really have to think about it. But long term, we're going to migrate the VHDL 2019 interfaces because they were designed with this use model in mind. The transaction API is a set of procedures that we call, okay? But they're not doing very much work. They're basically putting information into the record, and then they're signaling through this call to request transaction. They're signaling the verification component that, hey, I put something in a record. I put something out there for you to do. Go do it. And then this remains blocked until the verification component says it's done with whatever action we requested. That might be multiple clocks going by, but that could just be delta cycles going by. Okay. And then in this case, multiple clocks did go by, the operation finished, we get our data back. Okay, so we return results. We grab things from the record and return them as our results. Okay, so independent of verification component, we're putting things into the record, we're handshaking with the verification component, and we're getting the results from the record. So independent of the type of verification component it is. Okay, so we don't care if it's a UART or if it's AXI stream, it's the same abstract thing that we have here. All right, our verification component then. We have an interface to the dot. It might be a record as I've suggested here. It might be individual signals. For AXI bus, I definitely recommend records because there's a lot of signals that are optional that are very easy to connect if it's a record, very messy to connect if it's not. All right, and then we have the transaction interface. Okay, and a transaction interface in OSVVM is always a record type, similar to what we showed previously. Okay, so the verification component itself, it's a very simple blocking component, verification component, and that's where we start at. When we start our project and our design, we'll build a blocking verification component first, and then we might grow it into a more complex model from there as our needs evolve. Okay, so blocking is easy. We call wait for transaction that handshakes with request transaction that we did in the API command. And when we have something, we grab it and decode it. And we decode it, and if it's like an AXI write, we do that. If it's an AXI read, we do that. Mind you, AXI writes and reads, once you get up to AXIs, they are not blocking components. When we get into a full version of those, they need a lot of independent behavior. Okay. But the benefit here is that coding OSVVM verification component is well within the capabilities of any VHDL engineer. Note I said VHDL engineer and not verification engineer. The point being is your designers can do this. Okay, now, how do we simplify our verification component development? Well, first, an observation. Some interfaces do the same sort of transactions. Okay, and we've classified 2 so far, and we're open to hearing about more if you have ideas. But this is what we've got. Address bus interfaces, or if you prefer, memory mapped interfaces, such as AXI4, Avalon, Wishbone. They do things like reads and writes. Okay. Streaming interfaces, such as AXI Stream or UART, do things like send and get across the interface. And for that type of stuff, OSVVM has defined a library that we call our model independent transactions that define the interface and the transaction API. Okay, so the address bus, this is a minor subset of it. It has the record in it. It has the transaction procedures in it. Okay, the API set up for us. And again, as I said, we do a lot more than this. We do the bursting, we do asynchronous modes and that kind of stuff too. For stream, same thing. Define a record, define a transaction. Okay, and again, OSVVM has done this for you. It's an evolving thing. So if you come up with things we haven't implemented yet, we take pull requests, we take issues on, hey, I need this, okay, and we work on it. So benefits. Why do this? Well, we accelerate verification development. We accelerate test writing. We accelerate even our documentation. Okay, how does that work? Well, verification component developers, we reuse the library, the model independent transaction library, and hence we don't have to do those steps. Instead, we just focus on writing the verification component behavior, reducing the amount of work we have to do down to about the same amount of work you'd have to do if you wrote a procedure, except with a verification component, you get concurrency. So you get the independent behavior, something that can grow up into something that's much, much more complex than you can ever get out of a procedure. For test writers, verification components of the same class use the same transaction API. So we're not introducing for the UART, for AXI stream, different procedures. We're using the same procedures. And in fact, if we've written another layer of procedure calls that do a sequence of things, we can do that same sequence of things across any interface. So if you want to do like Ethernet across the AXI stream, and then you want to do it across the Avalon stream, you can use the same subprogram. Okay. OSVVM's co-simulation interface is built on top of the model-independent transactions. So we support any model-independent transaction-based verification components, including the ones you write yourself. Okay. Documentation, well, OSVVM is already documented in our model-independent transaction user guides what the transactions are that we support. So in our verification components, it's simply sufficient to have a table of this verification component implements these transactions from this user guide. Okay. All right, so our test sequencer, our next piece in our framework, is, again, it's where we write our tests. And on the entity interface of that, which we typically put in a separate file because there's one of those versus many test cases, it ports our transaction interfaces. So there are these address bus rec type and stream rec type. So in here, we have the whole test in one file. We have a control process that's responsible for initializing and finalizing our test. And then we have one process per interface, per independent aspect of an interface. For like a UART, we have a separate transmitter and receiver process, okay? Because those really are two separate things. And our tests just call the transactions, writes, reads, sends, gets, that sort of thing. So it's very easy to build up our directed tests. It's very easy. We build up our constrained random tests as a layer on top of this. OSVVM supports scoreboards, supports functional coverage. And of course, when we're going to run things as multiple independent processes, we need to support synchronization. And one of the synchronization methods we support is this wait for barrier, which is a software barrier synchronization, meaning when one of the processes get here, it stops until all of the processes that have called wait for barrier with that signal name also arrive at this point. And we do the same thing as we're ending the test so that we can get a synchronized ending of the test and do some good reporting. While the test is running, we're checking errors and accumulating errors in our alert log data structure. So when we get to the end, we can call end of test reports, and this is going to do a really good job reporting our errors and doing messages, creating the start of our reports, which the scripts will finish up for you. Okay. Initializing our test, we set the test name. We open a transcript file. When we just say transcript open without any parameters, it's going to create a UART RX1 matching the test name .log. And then transcript mirror says, well, as we're printing things out, when we open a transcript file, it says print them to the file. Transcript mirror says, oh yeah, also print them to console, please. So you get them. That's good for running debug simulations and such. All right. Next, we're going to construct some things. So our alert log and scoreboard data structures are singleton data structures, and we construct them just like you would if you were programming in System Verilog, except in System Verilog, right now you do them in a declarative region. VHDL currently says to call a protected type method in a declarative region is illegal, but it works in most tools. But I like being strictly legal, so I'm showing you this way of doing it. Okay, even though if you run in everything except, I haven't tried it in Cadence Excellium yet, and that's the only one I haven't tried it in yet. Okay. Our enables. So set log enables. This is for our messaging. Our messaging is off by default. This is turning on the pass flags. This is turning on printing info messages. But these info messages are just being turned on for one of the verification components, the one that has the ID that matches the RX ID there. And then we stop until the test is done. Or in this case, we gave it the extra parameter of 5 milliseconds. That says if 5 milliseconds go by, wake up anyway and return. And that gives us the ability to have a watchdog timer on our test and terminate it at that point. Okay. We'll finish up that process when we get to the end of this sequence of slides here. We make writing tests easy because all you have to do is call the transactions. So we're sending something to our AXI stream, perhaps. We call send. It goes through a switch and arrives somewhere else. And we do a get on that one. So we do a get to see, hey, what'd you receive? Did you receive what I sent? And we're checking it with a firm if equal. So firm if equal is one of OSVVM's checkers. One of the cool things about the checkers is they're logging the errors against our alert log data structure so that that report, end of test reports will report it. Okay, check basically replaces those 2 steps before there with 1 step. So that's a transaction that passes the expected information to the verification component and it does reporting for us. Speaking of the reporting, it looks something like this. This is the message that would come out of the test bench. I know that because it says NTB, the yellow highlighted piece there. That corresponds to the name that I created the test bench ID with. If for check, we might get a different, we will get a different ID for that one. Okay. So the benefits here, we've improved readability because we're using the transaction calls and we greatly simplified writing self-checking tests. Okay. Now, how about randomization? Okay, so the first question is, with any new thing, you should always be saying, why am I doing this? Well, if we look at a typical directed test, that's the top graph. And this is filling up a FIFO, by the way. You can see that we filled a FIFO, we emptied a FIFO. We're actually running it there with like 2 words in it for a while. And then we do some empty testing and full testing. And it moves a lot like a robot. Sure, it's going to hit all your points, but did you really thoroughly test the design? I'm not sure. And when we look at a constrained random test, we can see that with the same metrics, filling and emptying, it's much more covering the space. We do need metrics that are seeing that we're hitting those 2 endpoints, the empties and the fulls, and we have those there. That's what the other lines are, and we're counting them. Okay, so you need functional coverage when you start doing randomization. That's what's going on there. So why do constrained random? Well, it generates realistic stimulus in a timely fashion, meaning to write. We could, of course, reproduce the same stimulus with a directed test, but it's going to be tedious and take us forever to write it. Okay, and this is ideal for interfaces that have a large variety of similar items like mode, sequences, network packets, processor instructions, and that sort of thing. So it's not ideal for everything. Okay. OSVVM has a randomization library. Okay. And this is the basis for a constrained random. So we randomize with a range, min and max, or min and max and exclude. Or we use integer vectors as a set that allows the unconstrained array of integer vector to allow us to take a variable number of parameters. That's kind of cool. Okay. We do weighted distributions. A weighted distribution, here I'm specifying just a weight, 7, 2, and 1. And it's all about, I want to generate it some percentage of the time. And the percentage is determined by the total weight. So these add up to 10. So it'll be 7 out of 10, I generate the first number, 2 out of 10, the second number, and so on. And the numbers that I generate in this case are 0 to n minus 1. Okay, generally corresponding to the first parameter 0, the second one's 1, and so on. But that's a coincidence of VHDL. Okay. Or we can specify the number we want, 1, 3, and 5, and the weight, 7, 2, and 1 again. Okay. This by itself, though, is just a cute little randomization library. It's not constrained random. To get the constrained random, you have to add code patterns, and here's one code pattern. Okay, so code pattern plus randomization plus transaction calls, that gets us to constrain random. Okay, so first, let's randomize. So we're using distint. We're using quite a few more values, 70, 10, 10, 5, 5. And that says 70% of the time generate a 0. And we're going to use that to do in this case, a UART, and we're generating no errors. So we're setting flags that generate no errors. And we're generating a data value 8 bits, so 0 to 255. Okay. And then stop error. Stop error is good for demonstrating constraints. Okay, so one constraint we're setting is we're setting the flags to indicate stop error. The other thing, though, we change is data is no longer 0 to 255. It's 1 to 255. Because when you're generating a stop error and you're shifting out a 0 and you're doing even parity, that means parity is going to be a 0. And stop bit's a 0. That's a break error. That's not a stop error anymore. So we have to exclude that value, and that's the idea of constraints. Okay. And then we do our transaction. Here I set it up to do one transaction at the end. There's other patterns. We could, of course, been doing multiple transactions in each one of our case branches here. All right, what about self-checking? So far, what we've been doing for self-checking is mirroring, okay? And we don't want to do mirroring here because that's tedious and very potentially error-prone, okay? But instead, what we can use here is what's called a scoreboard. So a scoreboard is all about minimizing self-checking, the effort of self-checking when the data is minimally transformed. Okay, so internally, we have a software FIFO and a checker, just like the affirmative we had a minute ago. All right, and it uses package generics, so we can specify different types. And it uses subprogram generics, so you can tell it how to match things and all that kind of stuff. And through those subprogram generics, we can handle small data transformations, small differences between the input and output data. For example, in the UART, on the transmit side, we have an error injection code. On the receive side, we have a status code. And they're not exactly the same, although they're very similar. Okay, we can handle out of order transactions as well as drop values. Okay, well, how hard is this to use? And that's what it really comes down to is use models. And we want something that's at least as easy to use as System Verilog, right? Otherwise, we're not in the game. Okay, so we create a scoreboard. In OSVVM, again, we're working with ID types. Our ID types are part of our singletons. All right, and we call new ID. Again, we're calling it separately, but most simulators will let you call that new ID in the declarative region. Okay. And then to use a scoreboard, the first thing we do is push a value, and then we send it. We're putting the value that we're going to send into the scoreboard. So increasing the work on the transmit side a little bit, yes. But greatly simplifying the receive side. This receive side will work with any transmit side. Okay, so your transmit side could be doing something different than this. We do a get, we get the value, and a check into the scoreboard. Now, we said push first. The reason we push first is because the get side, particularly the UART, is center sampling and can finish a half a baud period before the transmit actually finishes. Okay, so the transmit doesn't finish until the last instance that the stop is set. So to make sure that the information is in the scoreboard before we do the check, we push before we do the send transactions. All right, subtle but essential. So all of OSVVM's data structures are singletons now. So our scoreboard, our FIFO, our functional coverage, our alerts, they use ordinary types. They all are named with the naming pattern ID type. And they use constructors. They all use the name new ID for their constructor. Our older methodology, not so long ago, around 2020 is I think when we added singletons, 2020, 2021, somewhere in there. Singletons require shared variables. Shared variables can't be mixed and require protected types. They can't be put in data structures. They can't be passed around very easily. Okay, so the singleton makes life easy. Okay, and we have them in our transaction interfaces. Okay, so functional coverage, what's it all about? Well, functional coverage is simply code that tracks items in our test plan actually happen. So it's an observer, and it tracks requirements, features, and boundary conditions. Okay, why do you do this? Well, if you're doing randomization, how do you know what the test did? Okay, Code coverage, yeah, that tells you some things, but that doesn't give you the complete picture. You need functional coverage to supplement code coverage to ascertain. Code coverage tells you, hey, everything ran. But what if your requirement was add another timer counter? Well, if you forgot to do that, you can still get 100% code coverage. Oopsie. With functional coverage, you'd be looking for, did interrupt 3 happen? That corresponds to the new counter timers. Okay. All right, so functional coverage is classified as item coverage or cross coverage. Item coverage, also known as point coverage in System Verilog, tracks relationships within a single item. Okay, so we're looking at the transfer size. So we're loading something into a register, and we're looking to bin it into small values, mid-range values, and big values, because we look at the details of small and big because that's where things break. The mid-range values, we can be as curious as we want to be about those. Okay. Cross coverage. Cross coverage looks at relationships between independent objects. Like we have 2 inputs to an ALU. It can both support selecting a certain set of registers. We want to make sure each set of registers has been worked, that comes from one input has been used with each set of registers that can come with the other input. Okay. Again, why not just use code coverage? Code coverage tracks code execution, but it misses anything that's not in code, including both of the examples up here. Okay. And you also have to watch your simulator, because code coverage is optimistic in some ways. It runs on every delta cycle, where what we care about is stuff that ran just before the last run of that process before the clock edge. All right, functional coverage with OSVVM is easy. Okay, I did this originally as a prototype to see what are we going to do next in VHDL. Turned out to be good enough that there was no reason to do anything more in VHDL. Okay, so we create step 1, create our coverage object. Again, it's a singleton. We then construct the data structure here. Okay, so this is constructing our shell of our data object that we can build things into, and then we define our coverage model with add bins and gen bin. Okay, in this case, the gen bin is very simple. It's generating a single number, 1, 3, 5, 7, and then a range, 9 to 15. Okay, and these correspond to the different values that we would get back from the status register of the UART. All right, and then the collect coverage we just call iCover. Okay, at the point of observation, and this is a point of observation. This is a good place to collect it. So functional coverage with OSVVM is as simple and concise as built-in language syntax like System Verilog and EHAP. Okay, and it's kind of cool because note that we're building it in sequential code, whereas System Verilog builds theirs declaratively. And when you build it with sequential code, you can use any sequential construct to help you, so we can use for loops and anything else the language already provides. Okay, so that's kind of a cool aspect. It makes describing complex functional coverage easier. Okay, so then we have this other capability that System Verilog and E don't have. Okay, we randomize across functional coverage holes. So the idea is that you set up the input perspective, you set up a coverage model that models the input perspective you want to see of a design, and you generate stimulus off of that. All right, so same steps we did before. We create our coverage object, we construct it, we define it. In this case, we're going to give things names. Okay, so I want normal operations correspond to gen bin 1, parity errors correspond to gen bin 3, stop errors correspond to gen bin 5, and so on. Again, these are matching status register values coming out of a UART. And then we call get ran point, randomizing across that model. These 7,000, 1,000, 1,000 are coverage goals. Okay, System Verilog calls them at least value. And we do too. We name them the same, even though they're really coverage goals. Okay, so we randomize across the coverage model. And then we're doing that same case statement, just with different values, 1, 3, 5, instead of 0, 1, 2, 3. Okay. And then we do the same thing. We push our scoreboard, or push our values into the scoreboard. We do our transaction, and we collect our coverage. Okay. This is recording coverage of operations that I'm doing. Note, to be able to do this, when I say send, the collect coverage here, it's not correct unless when I've proved that when I say send data in the operation that it does exactly that and nothing else. Okay. So inside of send, it can't do randomization. That will break the use model of calling iCover here. You'd have to call iCover somewhere else, such as we did on the previous slide, and that would be sufficient. Okay. Okay, so what we do with OSVVM's intelligent coverage goes beyond what other verification languages do by themselves. You have to go up to the portable stimulus standard with System Verilog, which is a whole nother tool and a whole nother cost basis. Okay. Okay, so for protocol and parameter checking, we use alerts. So for self-checking, we use affirmations. For protocol and parameter checks, we use alerts. So for example, in this one, we're looking at a memory model. And this is a very old static RAM memory model. It had a chip enable, a write enable, and output enable. And oddly, even though we had a single data line, write enable and output enable were separate and could be asserted at the same time. And that would be a disaster. So we have an alert here that anytime those change, wake up and check them. And if they're all one, flag it. And this catches them, even if they're all one, just for a delta cycle. This is the cool thing about having a verification component, because we put this in our memory verification component. All right. With alerts, they track the errors in the alert log data structure. So when we get to the end of the test, we automatically are able to report them. We have levels: failure, error, and warning. Error is the default, and I don't usually bother to specify it. I only generally specify it when I do failures. I generally don't do warnings. It's almost never. Okay. And then we have controls. We have stop counts. You get 20 errors, stop. By default, it's 2 to the 30th, 31st minus 1, I think is what it is, the biggest integer value. We also have a print count. This error is firing off so much, but I'm not paying any attention to it because I'm hot on the trail of something else. And I want to have it print to remind me that it's still there because I got to come back to it, but I want to ignore it for right now. Okay. And we can turn alerts off. Also, they're on by default, but generally we don't do that. Okay. And generally we make it very hard, even if you do this, to hide from it. Okay. Logs are all about conditional messaging. So we put in debug messages and then we comment them out and then we recompile code and all that. That's nonsense to do that. We don't want to be working that way. That's too hard. So instead what we do is we have these logs, okay, and they have a flag with them. And by default, most of them are disabled by default. So these only print when they're enabled, okay? So we have a set log enable. Again, they're disabled by default, but always, you can't enable or disable it. It's always on, okay? And then if the debug flag is false, then when we run that above code, it's only going to print the one for the always flag. Okay. And we can turn these on and off, enable and disable from any context in our test bench. Okay. And we can do them specifically for an exact ID also. All right. So this is the end of the sequencer part of things. So we wait for barrier and test done. Okay. We check, did we time out? Well, if we're at 5 milliseconds or beyond, we timed out. So flag it, just in case the test bench did nothing more than hang and didn't count any errors yet. Okay. Then maybe, not required, but maybe you want to end with all your scoreboards empty. So we check, is the scoreboard empty? If it's not, something's not checked, that's weird. Okay, so we can flag that as an error. We can also check, did you do any self-checking? Because what we're going to do when we call end of test reports is going to print a pass-fail message, and that's not appropriate if you haven't done any self-checking. So here, we're checking if there's any self-checking, and then at the end, affirm if not diff, we're checking 2 files. And if they're not different, pass. If they're different, fail. Okay, so this allows a checking of our transcript files, for example, or if you're logging interfaces and you want to check this interface versus a golden version of the interface, we can do that straight in the VHDL code. But warning, it only does a simple diff. If they're different by spaces, they're different. Yeah. And then we create a report. Okay. So this wait for barrier thing, we support two types. We support standard logic and we support integer underscore barrier. And it just magically works. Now, you do have to be careful of it. My recommendation is when you use the barriers, use a single signal for a single waiting point, unless it's only two processes that are communicating with each other. Okay. And this is nice because it used to be that we had all of our scripts had to know their run length. Okay. With this methodology, they don't need to know their run length. So each test itself manages its run length. We generally set the watchdog timer to be 2x or 5x bigger than we ever expected the timeout at. Okay. Okay, so shifting gears a little bit here. So prior to having scripting in OSVVM, I used a Tickle script, and Tickle script was awful. Okay, you had to be tediously detailed about things, and there was so much that I disliked about it and so much that other people absolutely hate about Tickle. So what OSVVM has done is, instead of writing our own language, instead of writing a text file of descriptors of things to do, instead of writing something that we're going to analyze ourselves, we put a procedure-based API layer on top of Tickle. Okay, so library is a Tickle procedure call. Okay, we say library to activate a library. What does that mean? Well, if the library has not been created yet, we create it. If the library exists, then we create a mapping to it. And then finally, we activate, we do what's called activating it. And by that, we just set this as the current working library internally, and then any following analyze command or simulate command uses that library. So you don't have to tediously and repetitiously specify that on every command line. I think that's one of the things many of the tool vendors got wrong about VHDL libraries. They really don't. The fact that they use work as a named library is like, it's horrible. So anyway, so what we're doing is simple. It's just like a list of source files that you had to compile, except what I found myself, when I had a list of source files that I wanted to compile, I found out how do I specify the library file? And I was doing stupid things like OSVVM_tbuart.lib, and then it would see the lib extension and say, oh, I need to, this is a library, and I need to do a library thing with it. Okay. Okay, so except we also get the power of Tickle if we need it. Hopefully we don't. Okay, hopefully you never need it. I seldomly use the extra power of Tickle, sometimes for a simple thing like an if statement. And trust me, you can learn everything you need to know about Tickle on Google. Okay, you just do a Google search, bang, everything you need to know is there. Okay, so settings like current working library, like the VHDL version you need to be using, it's all remembered. Okay, so we don't specify that in the analyze line or anything. And also, we don't want to specify it because then it gets tool specific, right? Paths. Paths are the big problem with Tickle. And paths in OSVVM scripting is all relative to where the script is at. So we call the script, and then any path in here now is relative to the script. So we co-locate our scripts near our source code with a relative path relative to our source code, making all the ugliness of Tickle go away. Okay. And we use one simulator scripting API for GHDL. It's a free simulator. NVC, that's another free simulator. Both pretty decent simulators. ALDEC, Active HDL and Riviera Pro, Siemens, Questa, and ModelSim, Synopsys VCS, and Cadence Excellium. Okay. Reports. And this is one of the selling features, I would say, of OSVVM. Okay. You got to be running, to get the reports, so you got to be running with RF scripting. I'm sorry about that, but you do. But it is well worth it. So we first thing you're going to see is as a single test completion message. The next thing you're going to see is when a series of tests finish, which is what we call a build, we create a mini report, but then we also create a build summary report in HTML. We create test case reports in HTML. So this is about each test case. The previous one was about all of the test cases that ran. And we also HTMLize your log file, which I didn't understand the value of that until I started running big regressions. And OSVVM log files can be 180,000 lines long. That takes forever to scroll. versus an HTMLized one where we hide things. I'll show you how that happens in a minute, making it very simple to even scroll through. Okay. We have our JUnit reports also. I'm not going to talk about those. Those are really not human readable. They're for the CI tools. Okay. And the CI tools take those and create a report that's not quite as good as the OSVVM HTML ones, but we do it because sometimes they pass the information from that report to something else, and that's essential. All right, so this end of test reports, the first thing you see that comes out of that is the test completion message. The %% done, passed, or % done, failed. Okay. And then next, we get our build summary mini report. Okay, this is just, it says build and then the name. And if there was an error, it says build error. And then it says the status, failed or passed. Okay, and then it says passed. This is the number of tests that passed and the number of tests that failed, the number of tests that were skipped, analyzed errors, simulate errors. We support skip tests because we run with different simulators. Some of the simulators don't support some of the stuff we need to do. Okay. And if there were errors, this is the first place we start to see something went wrong. If there weren't errors, we don't need to look any further. Okay. So if there were errors, then we dig into the build summary report. So the first part of the build summary report, sorry, this is coming up small, at least on our local screen, summarizes, this first thing is basically a superset of what we saw in the mini report. So it also includes like the tool name and the tool revision information in it. Okay, so you have that. The other thing in there is a link to the log file and the HTML log file. If you activated coverage with OSVVM, that only applies to Siemens tools and Albeck tools. We make that very easy because then each test case runs. We collect the coverage for that test case. For a test suite, we merge all that together. Then for all the test suites that ran, we merge that into the build coverage report, and then we run the vendor tools to generate an HTML report for it. And this is the link to that HTML report. Test suite summaries. So we divide our test cases down into test suites. A test case is an individual architecture. So a test suite is a gang of test cases doing something in common, like in our case, testing our AXI4 verification component. Okay. And then we have our test case summaries that give a listing for every test case, pass, fail. Okay. And note, if you can see the details on the slide, in front of each of those different aspects of this report, there's a triangle. Touch the triangle, it rotates and hides things or reveals things. You can see there we have, towards the bottom in the test case summary column, we have two things that are rotated and hiding the test case summaries from those. And that goes for all of OSVVM reports. We do that summary stuff to hide things. This is a test case that failed. So this is just to demonstrate how long is it going to take me to find things. Well, I see in the top of the test case report, hey, it failed. And then I go down to the summary table. Oh, this one set of test cases failed. AXI4 full. And then I go down, I can click on that. That is a link in that table there. I can click on that to get me down to this next table, and then I can find a test case in that table that failed. And then I can click on that and go down into the test case summary report. Okay, so this is the test case report. The first thing you're going to see there is a table of links. Okay, and then you're going to see the alert report. We're going to go through the details of this on the next slide. You'll note both of these are rotated. They're hidden. I think the first one's hidden by default. The second one's not. And then we have the functional coverage reports. These are all hidden. Normally they're not. And then we have the scoreboard report. We actually showed that here. Okay. So let's go into what each of these are. So the test case report in the PDF you get, you'll see both test case reports, the one with failed and not. Here I'm just showing the one that failed because it shows that you can track it right down to the ID, the alert log ID, where the failure was recorded against. Okay, to help you debug faster. That's the idea, right? That's why we do these reports. Our functional coverage report, what I was looking for out of this was something that competed with System Verilog, because we rightfully took a beating from our old text-based functional coverage reports. this brings us up to at least parity with System Verilog, if not a little bit better. Okay. And then our scoreboards. We tell you everything we know about the scoreboards, how many things flowed through it, how many checks were done there if it was used as a scoreboard, how many pops were done if it was used as a FIFO, and how many things were dropped, how many, you know, what's the current count in the FIFO. We want that current count to be 0. We want it to be empty when we're done. Okay. And we have a methodology to allow you to create your own scoreboards. And then for your own scoreboards, you'd have to call write scoreboard YAML to get it included. But if you use the right format, it's automatic. Okay. Okay, so we HTMLize your transcript, which means for every OSVVM step, we've put one of those HTML summary tags, and it tells you, okay, run test, and it ran. But if there was an error during a step, it factors that error out and prints it a second time in this file, so you can see, oh, there's a couple steps here that had errors. So if you're the type that just wants to scroll a log file, and you don't want to look at the stupid HTML tables because you hate HTML, fine, we got you covered. Okay, so we let you debug either way. I prefer the HTML, but if you prefer the HTML tables, but if you prefer just scrolling, that's fine. We're going to make that work too. Okay, again, everything's hidden here, but we gave you the ability to click on the simulation transcript in the test case, the detailed test case report, and it will actually jump you into this HTML transcript file with the information for this test case revealed. Okay, with that triangle for this test case rotated. Okay, I should mention that works in Chrome, that works in Microsoft Edge. Firefox has bugs and it doesn't work in Firefox, but I'm not the only one that reported a bug against it. So hopefully someday soon they'll have that updated. Okay, now how hard is it to get things? You can get things on OSVVM either as get clone, but make sure you do record cursive because we use submodules, and I just so highly recommend submodules and Git. They're awesome, and they've really helped with our development. But I also recommend you get a Git front-end tool if you're not familiar with it. I use SmartGit. If you're looking for one, I think it's pretty decent. Alternately, there's a zip file at osvvm.org. I know some people aren't allowed to go to GitHub, so we offer more than one way to get OSVVM stuff. To initialize things, I generally create a sim directory, and if you want to do that straight from your simulator console, you'll have to use Tickle. So you say file make your sim, CD into it. This is assuming that we're starting in the same directory as OSVVM libraries. Then if you're using GHDL, Siemens tools, or Aldex tools, you just source this file. There's a slightly different startup for Cadence, Excellium, and Synopsys, and NVC, see the user guide. Okay. And then you can do something like build the OSVVM libraries. So you just say build $OSVVM libraries. That means it's a variable. It's set by the scripts file up top. It knows, at that point, it knows wherever your OSVVM libraries is. Run the script OSVVM libraries.pro. And the other one is saying run all tests. Well, that's our regression test. You don't need to do that. You could run the demo test just to see a demo of things. And generally, for all our verification components, we use that same naming, run all tests, to run all the test cases. All right, so wrapping up, we have a very powerful and concise capability with OSVVM. It rivals other verification languages. So if you're a VHDL design community, you can be using VHDL for verification and get similar power to what other languages are giving you. We have unmatched reuse through the entire verification process. We have unmatched report capability with HTML for humans, JUnit XML for your continuous integration tools. Our tests are very readable and reviewable by all because we're setting everything up with transactions. And by setting it up with transactions, not only should your verification and hardware team understand it, but your system engineering team and potentially your software team also should be able to review the test cases. And for me, I'm always grateful because I worked in the defense community, and often those people would be invited to our reviews or demanded come to review. Sure would like them to tell me, hey, you didn't test this test case, because then I could test in the simulator and not end up with a bug in the lab. Okay. You can adopt OSVVM incrementally as needed. You don't need to grab the whole thing all at once, okay, or use all the pieces at once. And the other thing I'll make a claim to is the test and the verification components can be written by any VHDL engineer. What you need a verification engineer for is test planning. That's an art. That's a skill that has to be developed. But the mechanics of building out your framework, building out your verification components, writing your test cases once you have described what you need to do should be able to be done by any VHDL engineer. Okay. So just a quick commercial. SynthWorks does VHDL training. That's why we're in the open source stuff. And it's open source because that's the only way we can compete against things like System Verilog. Okay. So, but we do, if you want to get up to speed fast on OSVVM, we have our advanced VHDL test benches and verification class. It's in person, it's a 5-day class, and it's my favorite class at this point. So, we also have a number of resources about OSVVM. If you want to learn it on your own, we're cool with that. Most people don't, or most of the leading edge people might want to learn it on their own, and then when they're convinced that it's a good thing, they want the rest of their people trained, then they call us in. So as people are learning, of course I answer questions because they don't usually want to teach their colleagues. We have a forum at osvvm.org. Join us. You can also download. That's where the other place to download things is at. We have a number of recorded webinars. This thing you've seen is the first one. So this is the most recent version, and we're replacing that link soon. And then we have a number of other things. The second link needs to be updated too, because we have a newer one of that online at this point. Also, it was from the Verification Futures 2023 in June in UK. Okay, so thanks everyone who's attended. I can open up the floor for questions.
Hi everyone, session is open for question and answers. You can reach out.
Existing comparable to say something like CocoDB.
I haven't used CocoDB, but so the advantage of Python is that it has a plethora of libraries already developed for you, and but we have our C interface already, and it is possible you could use that C interface to drive Python through into OSVVM transactions too, in the same way that we're doing that. So I hope someday we'll have a Pi OSVVM that can connect, and if it could collaborate with CocoDB, that would be even better. So the disadvantage of CocoDB is, well, it's slower because you're going through that interface, and Python is slower. And you have to have one more language in your arsenal of languages you need to know. Now, if you already have a community that knows it real well, yeah, that's fine. But remember that verification is different than software development. It's not quite the same. Other questions out there? No, we're good? Okay. Well, thanks everyone for coming. And
yeah, thanks everyone. Thanks Jim for your valuable time. Yeah, thank you. Bye.
Bye everyone.